Okay, here's the start of Russell. The problem here says a toy car travels 6t squared plus 3 feet in the first t seconds after it starts. So imagine some sort of toy car, and this is the expression that's going to calculate how far the car has traveled. A way to ask for the average speed or rate of change for that car, which is the acronym here, AROC, average rate of change. You're given a series of what look like our coordinate points, but they're not. These brackets are basically to let you know that these are x values. They're both time. So after 2 seconds, we need to know how far the car has gone. After 3 seconds, we need to know how far the car has gone so we can start to work on calculating the average velocity of that car. Now on the graph on your second page there, I'm just going to give you a visual. After 2 seconds, which is here because that's your x value, that y value right there is how far the car has traveled. If we want to know how far the car has traveled after 2 seconds, we plug 2 into our equation. Our equation, which is 6t squared plus 3, plugging 2 into it, 2 squared is 4, 4 times 6 is 24, and 24 plus 3 is 27. So that right there is 27. So after 2 seconds, the car has gone 27, in this case, feet. After 3 seconds, here we have to recalculate how far the car has gone. So we plug 3 into that equation. 3 squared is 9, times 6 is 54, plus 3 is 57. So that right there is 57. So let's talk about what we do now. After 2 seconds, the car had gone 27 feet. After 3 seconds, the car had gone 57 feet. In that 1 second of time, from the second to the third second, how far did the car travel? The answer, 30 feet. Because it already had gone 27, then it had gone 57, so it had gone 30 feet during that time. So the average speed of the car during that 1 second is 30 feet per second. Now mathematically, what did we just do? We just did this. These are both x values, so you may want to rewrite them as coordinate points. We plugged 2 into that equation and we ended up getting 27. We plugged 3 into that equation and we ended up getting 57. If you haven't figured out what we've done already, we did this to calculate the average rate of change. We did difference of the y's, 57 minus 27, over difference of the x's, 3 minus 2, which got us 30 over 1, which was 30 feet per second. Now, what we just did here, since you do difference of the y's over difference of the x's, is found the slope of this line right here. The slope of the line that connects those two dots. That's what we just found. So we can find the average rate of change for all of these dots right here if we just think of them as x values of coordinate points. So for each of these, take these two numbers here, make them x values, calculate their y values by plugging the numbers into the equation. In this case, 2 we know is 27, and in fact all of these have 2, 27. 5 we plug in there, we square it, 25 times 6 is 150, 150 plus 3 is 153. And we're just going to do difference of the y's, start with the largest y, over difference of the x's. Remember, if you start with the largest y, you're going to start with the largest x. And we're looking at 126 over 3, 42 feet per second. And what that is the slope of the line that connected 2 to 5, which is way out here. That was the 153. We found the slope of that line right there. Oops. And it is steeper, and steeper means the speed is faster, and that's why our rate was higher. So what you need to do right now is calculate basically the slopes of all these problems right here, with all having 2, 27 in common. So you need to calculate the other y value right now. for the second x value and do difference of the y's over difference of the x's.